inductor, we'll go to the our new topic. So let us first complete this inductor. So first is like we have done for your capacitor. Now similarly we'll do source free RL circuits. Okay. Now what do you mean by source free RL circuit? So as I discussed earlier, if you have a inductor and then you have here a resistor, you have a L, you have a R, and then you have this is the ground. Okay, so some source is there, and by sourcing you are flowing the current. Okay, so you know this is also memory element. Like in the capacitor, voltage cannot drop suddenly to zero, cannot increase from zero to some voltage, and suddenly it cannot drop down to zero arbitrarily or abruptly. Similarly, here the current cannot uh, go down abruptly. It cannot go from high to zero directly. It cannot go zero to high directly. And similarly, high to zero cannot go. Okay, so the current will decrease with time. So voltage across the this one uh, remain. Current will remain here. So voltage will be also there because there is always change in the current, and we know the voltage across the inductor is given by L di by dt. So current slowly reducing. So there is a di dt component. So there will be always some voltage. Of course, as the rate is decreasing, a constant depends. So voltage will be also decreasing. Okay. Now what happens whenever I told you the inductor, the property is what? Whenever you try to flow any current, okay, it will always oppose the effect. Now initially current is zero, you are trying to put a current I, okay, directly from zero to I, okay, so a voltage will develop and that voltage will oppose this change. So the sign of voltage will be like this, okay, the voltage will oppose this current. So it will try to balance this current, okay, it will oppose this current. Okay, oppose this current means it will give some resistance, some reactance, so that it should not increase. Okay, current should not change. Now similarly, now if the current start reducing, the current start reducing, again a voltage will develop. Okay, the sign will be opposite. It will oppose the decrease in the current. Okay, so now this is source free circuit because it is the current is decreasing. The voltage sign will be like this. So here will be voltage, and this will be your VR. You can write like this also. If you want, you can put a VL here like this also, because this voltage is this voltage, but then this voltage will be here, DIT will be negative. That you have to understand. Okay. So other any way you can understand this thing. Either you keep this VL equal to VR, because voltage across here and voltage equal to will be always same because both are parallel. Okay, but then here you understand this DIT is negative because now current is decreasing with time. So now you can write here either apply KVL. Now suppose because you have written like this, so you can directly write VL equal to VR. Okay, and now if you write oppositely plus minus here, then you will write plus VL plus VR equals to 0. Here DIDT will be positive. Okay, that difference you will understand the way whatever way you write, you to understand that one. Here it will be always opposite to this one. Sign will be opposite to this one. Okay, so if you write so this is your VL. Now if suppose you say now I will write like this because this sign should be always opposite in nature. Value should be same. Okay, then you write this one. Both are same thing. Okay, so the VL is what? Minus L di by dt, and this is what? IR.
I into R.
Okay, so you can write now again. If you would make it here, this become L di by dt plus IR equals to 0. Same equation. Okay, there this is positive. Same equation. Same, the meaning is same. That you to understand what you the way you would write. Okay, now solve this equation for I. So L. So I can write here only here itself we can write di upon I. Okay, minus R by L dt. Okay, and initial current, you should know initial current. You can assume something
0.
I naught. Okay,
I
so say
naught.
so initial current I is at t is equal to 0 is I naught. Using this boundary condition, if you solve this equation, this will give you same equation I naught equals to minus t by tau. Okay, and now tau will be what? Tau will be your L by R. Okay, time constant of the circuit. You can solve this equation, the same equation will come. Time constant. The rest is everything same. Okay, so what you done in the capacitor. So let us understand this with an example. So this is source free circuit. Okay, so here initial current is I naught, final current is 0. Okay, so you say this is plus minus 40 volt resistor. Here you have a resistor 12 ohm, 2 ohm, 4 ohm, 16 ohm, 2 Henry. Okay, now you want to find current I as a function of time for time t greater than 0, because at t is equal to 0 time you are opening this switch. Earlier switch was closed and now t is equal to 0 you open. So find out first initial current and then IT. This is IT. Okay, so first is find I naught. Okay, when you opening the switch, that time what is the current here? So initially it is close, so put it close. So now how much current is there? This is the inductor. For DC, this will behave like a short circuit, and you want to find how much I naught is there. Okay, so if this becomes short, obviously this resistance also becomes short. Yes or no? If this is short, no current will flow here. All the current will come here. So this resistance will not be in calculation while calculating the current. Okay, so this becomes short. Now I naught will be how much? Tell me. कितना होगा I naught? Now this 4 and 12 become parallel. This 4 is now parallel to 12. 4, 12, 16, 1, 4, 3, 3 ohm. And now 3 plus 2, 5 ohm. So 3
8
plus
ampere.
5 ohm. So my I naught will be 40 divided by 5. This will be 8 ampere. So I know this I naught. Now the second part is that you have to remove this circuit. You have to open this one. So once you open, this circuit will be removed. This part will be removed. And now you have to connect back your all the resistance. What is the value here?
16 ohm.
16 ohm. Okay. Now current will decrease. Now current will change the sign. IT will be like this. Okay. And this portion you are removing, this disconnecting. So you can remove this one. So now you can find IT. So tell me, what is IT? Okay. So first you have to find the R equivalent for this circuit. It's coming uh, 8 or 6. Just give me 1 minute. Have you done any mistake while calculating
4 I
the
naught is coming out to be 6 ampere.
uh, that's how do what mistake we have done? Tell me. Did I do something wrong? Because 4 and 12 was in series, okay, parallel. 16. So this was 4, this is 3. It was 3 ohm and the resistor was 3 and 2, 5. Total current was it was I naught. Okay, sorry, correct. So this is 8 and 3 plus 2 was 5 ohm. Okay, this was total current coming here. This resistance was not there. And now you have to find the current in the 4 ohm, that is I naught. First you have to find I naught. So I naught will be, you should people tell na, keeping this total current is I. So I is what? 40 upon 5, 8 ampere. And now I naught will be, will divide here and here. So this will be total current 8, opposite resistance 12. Okay, and sum of resistance 16. This is 1, 2, that is 6. So I naught is 6 ampere. Okay, and now you will remove the circuit, and now you have to find second, you have to find the IT. So this analysis for t less than 0 time. And now second analysis for only this will involve this circuit and repeating this thing again and again. If you're not getting, still not getting. Okay, now the next circuit is this is for t greater than 0 time. And now find the IT, find the R equivalent.
1.6.
So R equivalent will be how much first? R equivalent will be voltage resistance across this one. So this is 16, 16, 8. Okay, R equivalent will be 16 parallel to 16, that is 8 ohm. And tau will be your L by R. L is not given, so L value is 2 Henry. L value is 2 Henry. So 2 Henry L by R 8. This is 1 by 4. Okay, and now you can put it here. That's it. IT will be 6 e power minus 40 ampere. Let me do one more problem. Shall I erase this one? So this is your plus minus 10 volt. This is 2 ohm. Okay. This is 2 ohm, 3 ohm, 6 ohm, inductor 2 Henry. Okay. Now at t is equal to 0, t is equal to 0, I am closing this switch. Before that it is open. Okay. So when it is open, initially it is open. So when initially open, tell me how much current is there in the inductor. This is 6 ohm, this is 2 Henry, and this is 6 ohm. How much the current is there in 2 Henry? That is find I naught.
0.
No, I naught, I naught. How can it be 0? This is short circuit. This short circuit means this will be also short circuit. This you can remove. Now how much current is flowing here? I naught. It is open. Initially it is open.
So 2 ampere.
2 ampere.
So I naught. So this current is, which current is coming here? That is I equal to total current is I naught is equal to I naught here, which is 10 upon 5. That is 2 ampere. Okay. Now the next thing is, what is the next thing? Next thing you have to close this switch. So next part, this become close, and this become your inductor. Okay, and here you have a resistance of 6 ohm. Now if this, once this becomes short, no current can go here. Yes or no? Can current can go here, this part?
No, sir.
Because this becomes short. So now this source is not having any influence on this inductor. That means this circuit now becomes source free circuit, because once voltage is not giving charging or not giving any current to inducing any effect here, not giving current here, now it will start discharging. Okay, so this circuit is no use. Okay, so this circuit is, you can say this circuit is not involved here in this, for this circuit. So your final, so this is so this is for t less than 0, and if you find t greater than 0, your circuit will be only 6 ohm, inductor 3 ohm, this is 2 Henry. So you can find now R equivalent. R equivalent is how much? 6 parallel 3. This is parallel to this one, and this parallel to this one. You have to open this one. Okay, finding the R equivalent, you have to open this one. R equivalent. This is 3 parallel to 6. That is 9. 3, that is 2. 2 ohm, and tau is your L by R. L value I given you how much Henry? 2 Henry. Okay, so 2 Henry, and R is also 2. This become 1. So your I become I naught, which is 2 e power minus t ampere. Okay. So this was source free circuit, and now you can, so this is where initial current is there and final current is 0, but initial current is something else, and is one thing, and final current also present. both have different values like we have done in the case of capacitor, then the formula remains the same. What will be the formula? So IT will be what? IT will be, tell me, what is IT? Second case, I infinite plus I naught minus I infinite e power t upon tau. This will be the current equation. Okay. Either you write like this, sometimes you write also like this, IT equal to I infinite plus I0 minus, if you follow the standard book notations, and then this is the equation. So let us use this equation also. Say you have a circuit plus minus 10 volt. Okay. And then this is your 2 ohm and 3 ohm. 2 ohm, 3 ohm. And here you have a switch which is get open. Is get open at t is equal to 0 time. Okay. Before that it is closed. So this is basically opening at t is equal to 0 time, and initially it is closed, and you have here 1/3 Henry. This is my circuit. Now, so for t less than 0 time, this circuit is closed. So make it close and solve. Find I naught and find then I infinite. So for t less than 0 time, this circuit is closed. So I'm making this close. If you have done, if I made the circuit, okay. So 2 ohm, 3 ohm, and now you make this is become short. Okay. Tell me what is I naught? What is I naught here?
Sir, 5 ampere.
So this becomes short. So this circuit will, so current will come here and current will directly come here. So only resistance. So this is 0 resistance. So you have only 2. So I naught will be 10 divided by 2. That is 5. Very good. And now you will remove this one for t greater than 0 time. Now what is I infinite?
2.
Okay. 2. So this is now 10, 10, 2, 3, 5. 2 ampere. Okay. So your equation become IT become I infinite, which is 2 plus 5 minus 2. Okay. And now you want to find the R equivalent also. Okay. Across this one. So you have to make this short circuit. This is your final transient circuit. So R equivalent will be how much? Tell me. R equivalent is 5.
5 ohm.
And tau will be L by R. L is 1/3, that is 5. So 1/15. So my equation become e power minus t by 1/15. That will become 15. Okay. So IT will become 2 plus 3 e power minus 50t. There's a time as a function of this one. You can you can recheck also whether this equation is correct or not or wrong. But easily you can check, because here you have a 10-volt source. You have a 10-volt source here. Here you have a resistance 5 ohm. This is removed in final circuit. So of course you can check what is the value of I naught also with at t is equal to 0 with this equation. That will come same like. And now you have here is an inductor. Inductor. Okay. So inductor is what value is your 1 by 3. And now you can check whether this equation is right or wrong. If I write the KVL here, this become 5. So I can write minus 10 plus 5i plus 5i. Okay. This if I current is flowing, and then here voltage is how much? This voltage plus this voltage, and plus K, if you're at KVL, plus minus plus L di by dt. Okay, so I'm writing again, this is a minus 10, and this is V equal to, this is VR 5 VR, and VL equals to 0. So minus 10, so 10 equals to VR plus VL equals to 10. VR is 5i, okay, and VL is your L di by dt equals to 10. Now you can use this equation, put it here, and check whether the left hand side equal to right hand side. So you have a 5, I value is what? 2 plus 3 power minus 15t plus L is 1 by 3. Differentiate this equation, di by dt, how much will come? Minus how much? 45 e power minus 15t, okay, equals to 10. Solve this one. So this will come, solve this one, how much coming, tell me? L di by dt. So this will give you how much? 15. 15 will come here. This is minus 15 plus 15 will come here. So this is 10. 10 equals to 10. Hence proved. So this equation is correctly satisfying this KVL also. So meaning is basically if you solve this equation, okay, this equation, knowing the initial condition, okay, you will land it this equation. That is the meaning. So either you solve differential equation, okay, writing KVL differential equation, or directly the way I told you, you can, that is easy method. So you can solve any complicated circuit using this way. Because finally the equation is this only. So these are the equation of this equation only.
Sir, actually, these are alternative.
Huh. Alternative ways, yes, you can say.
Okay, sir.
Okay. So this is your circuit analysis is complete, not completely complete, but now we can move on. And wherever we require some more skill of network analysis, we will be keep on discussing with time, like AC circuits. AC circuits are very easy. Okay, there is only some variation. So we learn while moving. Okay. Now we can go to the diode. Okay. And before we discuss diode, it is necessary that we should understand what is PN junction. Okay. So let me discuss now PN junction. So have you done the semiconductor chapter in solid state physics, or there is only electronics going on?
No.
So you're not done in semiconductor. So the semiconductor detail, Kunal sir will tell you some derivation part on that is common between electronics and that one. Okay, earlier I was checking, so you can check that material. In material, everything is derivation is everything is given. Okay, that is prepared by me only. Electronics. So that is nicely every aspect is given. So here I will not discuss the derivation part because electronics I don't need those equations, but qualitatively I will discuss some derivation also. I will do it for you. Okay, and now we'll just qualitatively because I want to use a PN junction in the electronics. Okay, so PN junction is what? PN junction is a basically diode. So we should have some information, some knowledge about the PN junction. Okay, so PN junction, as you all know, that is made of P type of semiconductor and N type of semiconductor. When we bring a P type semiconductor in contact with the N type of semiconductor, okay, or we joined, okay. So actually, in practical, in the reality, we don't join them, okay. If we have somehow uh, uh, create a junction, okay, between P and N type of material, that is generally happen through ion implantation technique, okay, or diffusion process. So that we are not going how PN junction is formed, but that is the fabrication part. So we have to create a PN junction. So there's one part is P type material, P type semiconductor, other part is N type of semiconductor. Generally of same material, it may be different also, okay. But now we will first discuss what is P type material, P type semiconductor, N type semiconductor, okay. So let me discuss first semiconductor. Now semiconductor is a very important class of material, okay. It has some properties which because of that all the electronic devices are made of semiconductor, okay. One that property is doping. You can create a different kind of uh, or some versatility in a material, in same material, a host material, you dope, you can change its electronic structure, okay. You can make it P type, you can make the N type, you can shift their Fermi level, okay, significantly. You can bring the you can move the movement of free level, Fermi level in a semiconductor. That's why this is very interesting material, okay. This is not possible in the case of metal. However, metal has a higher conductivity than semiconductor, but you cannot create devices out of metal. Okay, that means so many useful devices. Semiconductor, all the devices are made of semiconductor, like PN junction, hai, transistor, hai, MOSFET, JFET, tunnel diodes, LEDs, solar cell. Everything is made of semiconductor. Okay, so because of it has this material has some capability means you can modulate this material, okay. You can vary its conductivity, you can play with its electronic structure, and that gives us capability to form the devices. So let us first discuss in the simplest way, okay. Semiconductor, basically we can convert them in P type and N type, okay. So this is the semiconductor P type, and there is a N type semiconductor, okay. You can convert them. Pure semiconductor, these are doped semiconductor, these are doped semiconductor, doped, okay. And undoped or pure semiconductor, there's a pure semiconductor, and there are doped semiconductor. Doped semiconductors are two type, P type, N type. And pure semiconductor, generally we call them intrinsic semiconductor. Intrinsic semiconductor. So a host means the as it is without any modification. Okay. Example of semiconductor. Can you give me the example of semiconductor material?
Silicon or germanium.
Okay, silicon, germanium. These are intrinsic semiconductor. Okay, silicon, germanium. These are elemental semiconductor. There are compound semiconductor also like gallium arsenide. Okay, there are many aluminum gallium arsenide, alum, aluminum gallium arsenide. So these are compound semiconductor, two element compound, three element compound. Okay, this is elementary. So semiconductor main property is the some basic properties are that it has a band gap. Okay. Now let us understand what is p-type material and n-type material, giving the example of silicon, because we will take elementary discussion, because your course is like a basically fundamental course. Okay. We will not go in compounds and depth everything. Okay. So we'll just discuss what is silicon and germanium. What is this bonding structure and how can you convert them in p-type and n-type. So p-type means you have to dope the impurity. What is the impurity? If you intern semiconductor doped with a wait
So
third group
30
impurity, third group impurity, third group impurity. What is third group impurity? Aluminum.
Trivalent.
sir, sir, last shell 3 electrons are there.
Three group
Trivalent.
means it's a well as three. So example of aluminum, gallium, or
Cesium.
in huh?
Cesium.
Cesium is third group. Okay, you would check. Okay, so basically aluminum, indium, and here the n type means the doped with fifth group element. Fifth group element. Fifth group element. Fifth group element is what? Fifth
phosphorus,
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 arsenic,
arsenic, and
arsenic,
antimony. Potassium.
antimony. Okay, so this some example you have to remember. Okay, now let us understand what is intrinsic semiconductor. What is, I'm not going in depth. I will focus only my distinction part where I need for electronics. Okay. Now, what is intrinsic? Intrinsic means, for example, I'm taking a your intrinsic silicon. Okay. So intrinsic silicon has a band gap of say 1.1 electron volt. Okay, so band gap of 1.1 electron volt. So and intrinsic carrier concentration has say 1.5 to 10 raised to power 10 per centimeter cube. This is the intrinsic carrier concentration, how much carriers are there in intrinsic semiconductor. Okay, so if I draw the band gap, so this is the conduction band. Okay, bottom of the conduction band and is the top of the valence band. Okay, and the gap between these two is called Eg, band gap. Okay, band gap of semiconductor. So here you have a conduction band and here you have a valence band. Okay, this is the electronic structure, but as physically, if we try to understand silicon, so silicon is a fourth group element. Okay, fourth group element. Fourth group element. So when I say it is a fourth group element, okay, if I see its structure, this is my silicon. It has a four band, four. So here you have electron here. So it has a four electron it is sharing with neighboring atoms. So this is the basically crystal of silicon, which is basically silicon atoms are bonded with covalent bond. Okay, this is a covalent bond. So this is the structure is keep on moving. Okay, you can further you can plot, keep on this one. Okay, now this is silicon, and now these all are valence electron. Okay, so this is your valence band. So these electrons, if I see at the electronic band, these electrons कहाँ पर बैठे हैं? These electrons are sitting here. This is sitting here. These electrons are sitting here. Valence band. Okay, this electron is basically sitting here, and here there is a no electron. Okay, here we don't have any electrons because it's an intrinsic semiconductor at T is equal to 0 Kelvin. This is the case at T is equal to 0 Kelvin. So T is equal to 0 Kelvin, intrinsic semiconductor valence band is completely empty at T is equal to 0. Conduction band is completely empty, almost empty. Conduction band is almost or complete. You can say completely empty. What is wrong? Conduction band is completely empty. So when conduction band is completely empty, your intrinsic semiconductor behaves like an insulator. Okay, so intrinsic semiconductor behaves like an insulator. Okay, it behaves like an insulator. Now this is not useful, okay, because your material should have some conductivity, okay, because if you want to use for devices, so this type of semiconductors are not useful, practical useful. Okay, of course you can make a device, you can operate them at high temperatures, okay, but at working temperature, that at temperature what we use, we do operations, okay, that is room temperature 25 30, somewhere temperature is high, okay, summer temperature is low, winter temperature is low, something 5 Kelvin 10 Kelvin. Okay, so that range, not 5 to 10 Kelvin, it's 5 degree centigrade, 10 degree centigrade. Okay, that not that much low. If you go low, then you require some special modification of the materials. But the working range where we human being operate devices, okay, for those temperature ranges, these type of semiconductor are not useful because their conductivity is almost zero. T is equal to 0, it is 0. Okay, but the operating temperature, like if I want to make this is at 300 Kelvin, so then you have some conductivity, but that is also not useful. So say for example, if I say this is if I make this T greater than 0 Kelvin, okay, or say I am plotting at room temperature, say 300 Kelvin room temperature. So if this much energy I supply, okay, this much energy means this much energy is equal to what? KT. This energy is KT, thermal energy, KT. This is 1.38 into 10 raised to power minus 23 joule per Kelvin, and this is 300 Kelvin. So this will come out how much? Can anyone remember this value? What is the value? It will come out around 259 if I convert in electron volt, milli electron volt, okay, or 0.025 electron volt. 0.025 milli means point to 25.9 milli electron volt. So this become 0.02559 electron volt. Okay, exactly you can calculate. This is the value what I remember. 25 milli 25, correct. 25. So this now this energy is how much? This is very low compared to the band gap. Band gap is how much? Band gap is 1.1 electron volt, and this energy is say milli electron volt. So even if you are increasing the temperature, there is no possibility that this can go here because of this energy. It cannot go here. Okay, but even though somehow these electrons reach here, so at high temperature, zero temperature, they cannot reach, but higher temperature, these can move here. Some very few numbers, say 1% or less than 1%. Say, so the 4 electron can reach here. So there will be 4 holes will be created. And the number of holes in intrinsic semiconductor and this is the number of electron in conduction band, and pi is the number of holes in the valence band. Okay, or or you can write n0 p0 in equilibrium. So that n intrinsic pi intrinsic, okay, both are same, and this intrinsic carry concentration at room temperature at 300 Kelvin is given by 1.5 10 to the power 10 electrons per centimeter cube. If you take is per centimeter cube of block, this will have a this much electron. Okay, now 1 centimeter cube if you take a crystal, okay, how many atom will be there? That you can find if you know the density of crystal, and if you know the mass of the crystal, okay, and you know the atomic mass, you can find how many atoms are there, and out of those the number is very high. Out of that atom, some every electrons, if the electron of so some electrons can come. Okay, every atom has a 4 electrons sharing. Okay, so some of this electron can come here, and that this make this number 1.5 to 10 raised to power 10 per centimeter cube. Okay, but this number still is not very sufficient, and I told you this energy is not sufficient because this gap is very high, but until some may reach, because that is the quantum mechanical phenomena. Even though you have a less energy, still you have a potential, still there is a probability that you can jump through a barrier. So if even though this has a very low thermal energy, but they still can reach here either quantum mechanically, or either you can say that this is the thermal energy. What about the light energy? Okay, because you are not doing the experiment in the dark, na? Whenever your material is there, crystal is there, that is kept on the light. So some light photons are also falling, and light photon have energy very high, 3 to 4 electron volt. So at least 2 to 3 electron volt. UV has a more UV photons. So then photons are forming, IR also forming temperature. Okay, and because of that one also, some of may can reach here, and you have a conductivity, and this is the case of host material, a crystal which may have some impurity. So some impurity will be there, some breakage, some irregularity, something will be there, and because of those all combined together give you some electron, some defect levels are there. Defect levels means some defects are there, some these are missing, or some other extra impurity, some impurity will be there. Minimum impurity will be always there whenever you take this material from the this when you dig it from the dust. Okay, so there some electron may reach here. Some probability is there. Okay, so these are your intrinsic semiconductor, but that are not useful for us. So what we convert, we make a doped semiconductor. For example, if I want to make a n type of material. Okay, so for n type of material, what I will do, I will replace this I will replace this while synthesis, or while diffusion. I will remove this silicon. I will replace one more atom instead of silicon while doing in the synthesis part itself. Okay, I'll put some impurities. So along with silicon, I put some impurities also. So 1%, 0.1%, or 1%, 2%, very less number. Okay. For example, if I say what is Avogadro number? 6.6 into 10 to the power 23. If I take 1% of this one, so 1% will be how much? 1% will be itself also 10 to the power 21 atoms. Okay, so not that very less percentage, very less. Suppose if I put the impurity in the order of 10 to the power 10, actual atoms are 10 to the power 23. If I put 10 power 10 atoms, okay, through this crystal, so this some of the silicons will be replaced. Now, for example, if this is a fifth group element, now one electron will come here. This is the free electron. Okay, now how does this free electron, and this is very feebly connected, this is very low, it's a weak force. Okay, so this you can make very easily free, and this free electron, this electron, extra electron, can reach to the conduction band, and it can enhance our conductivity. So let me tell you how it happens. So for example, this is your conduction band and this is your valence band. Okay, and somewhere here is a Fermi level, which we call intrinsic Fermi level. But here that you draw intrinsic semiconductor, you also draw a Fermi level, which is the middle of the band gap, that will be discussed in the solid state physics part. So this is the intrinsic case, Fermi level is here. Now what you do when you make a n type of material, okay, so here you have a valence electron. When you dope, you don't change the band gap. Band gap remains the same. Band gap remains the same. So here you have valence electron. Okay, and some of electrons already at room temperature. Some of electrons are already here. So four electron here. 4 holes are here. But what about this electron? This electron is different than this electron. Where is this electron? This is the impurity level, and impurity level atoms are sitting here, very close to the valence band, very close to the valence band. This is called impurity level. This is called impurity level. Now what does mean by impurity level? Okay, so whenever you dope this P here, now if I give some energy, this electron will become free. That means the first ionization, this is also atom, and this electron belongs to this atom. This electron should be somewhere in the atom. Okay, and now I'm giving some energy and it makes free. That means this is the first ionization energy of this electron. Okay, impurity atom. So this ED is this gap is the first ionization energy. If I give this much energy, so electron sitting here, that means sitting here to the phosphorus atom, okay, can go here. So here all the doping atoms are sitting. So generally this is dopant, and dopant we denote by D. So this is the ND. So all the dopal atoms like phosphorus atoms are sitting here. So I will denote them by ND. I will denote by them Nd. Nd is what? Nd is the dopant concentration. Nd is dopant concentration, how much concentration atoms you have produced, and every atom is giving one electron. So either you put Nd, or you put the name of the phosphorus or arsenic, like like suppose if I use the arsenic here, so I will write arsenic here. Here arsenic is sitting, arsenic atoms are sitting, arsenic are sitting, arsenic are sitting, arsenic are sitting, and now you give this much energy. This energy is in milli electron volt. So the energy what we are supplying to the semiconductor, that is sufficient to make this ionize. So this all atom will get ionized. Okay, and the concentration of this atom is Nd, and this atom will, when ionized, their electron will reach here. These electrons will come here, and these electron numbers are very high compared to these electrons which is coming from the valence band. So these are arsenic atoms. These are arsenic atoms. Okay, many concentration is 10 to the power 10, 10, 15, 20. Okay, in this number is 10 to the power 10. So this may be 10 to the power, this number may be 10 to the power 12, 12 or 13, 14, 15. So compared to this number, these numbers are very small. Okay, you can neglect 0.1%, 1%. So this number will dominate. So now you have a lot of electrons. Okay, and now this is ready for conduction. This is the example of n-type semiconductor. Okay, and the Fermi level of n-type material lies close to the conduction band. So basically, this thing will understand detail in the semiconductor solid physics. So here you have a EC, you have a EV. This is the Fermi level of n-type material. This is the dopant level. So Fermi level is very close to the conduction band in the n-type material. Okay, close to n-type material. Now, I will not go much detail. I will just try to come on p-n junction. Now, similarly, I can say what is p-type material. So n-type material is the majority charge carriers electron. Okay, so these are the majority charge carriers. Majority charge carriers. These are electrons. Okay. Similarly, let me discuss now p-type material. So p-type material, this will be replaced by aluminum. Okay, and I'm rubbing this one. So in p-type material, this is your EC, and this is your EB. Okay, here you have a valence electrons. This is your EG. And now acceptor level here, aluminum atoms are energy levels are somewhere here. These are aluminiums. Aluminiums means there is a first electron affinity. They can capture the electrons. Okay, they are acceptor atoms. These are acceptor level. This is the acceptor level. That is also donor level. This is the acceptor level. Acceptor level. Okay, and now they can take this electron, so they will become negatively charged. So when they become negatively charged, there you create holes, because these electron gone to this aluminum. They are capturing this one, the third. So here you have some hole present here. This hole is in the valence band. Of course, these some electron can go here. So here, say 3 electron going, so 3 holes are there. But majority of holes are coming because of this impurity. And this is the majority charge carriers in p-type. This is the p-type. So this is your majority charge carriers. Majority charge carriers in p-type material, and this is your acceptor level. Okay, now I will not discuss much. Now you have idea that donor atoms becoming positive charge and acceptor atoms are becoming negatively charged. Okay, they are ionized, and this one thing is you have clear in mind. And second thing, you have a clear in mind that p-type and n-type have a higher conductivity compared to the entrance part. P-type have a high amount of electrons. Okay, majority charge carriers, high number of electron concentration, and p-type has a high number of hole concentration. These three things you know, and now I can go to the p-n junction. So I'm erasing this one. Can I erase this one?
Yes, sir.
Yes, sir.
Now for representation, okay, because I need to communicate. Okay, so there is not necessary that I should make a p-n junction is a p-n junction. Okay, if I keep in front of you, that will look, you can look at what is p-n junction, but just for literature and communication purpose, we have to draw the p-n junction on the board or some on the book. Okay, so how to draw a p-n junction for understanding and for communicating the information? So generally, if you want to draw a n-type semiconductor, so n-type semiconductor are denoted by its impurity, because impurity is fifth group element, and that fifth group element is capable of giving electrons, so that make it ionized. So I can represent this is the n-type material with a plus sign. This is not a hole. This is the ion fixed in the lattice, because fifth group element impurity get ionized. This is the donor ion, okay, or donor impurity. Donor impurity. It is the, these are the lattice points, atoms fixed in the lattice. These are fixed in the lattice, fixed in the lattice. Okay, and they all have some electron which they can release, and they will become ionized only after releasing this one. But it is a loosely bound, so I can represent like this. So these are electrons. These are loosely bound electrons. And this is the schematic representation of a n-type material. This is an n-type material. N-type material, which has the impurity concentration is how much? Concentration is Nd atoms per cc. And assuming each atom will give, assuming each atom will give one free electron, assuming each electron will give one free electron, I can say the concentration of electron is how much? Nd electrons per cc in this section of per centimeter cube of section of this semiconductor. Nd is the concentration of electrons, which is Nd. So either you draw n-type material like that. Some book draws n-type material with only electrons, but that schematic is not useful. We cannot get a useful information. So I will always draw n-type material like this. Okay. Similarly, if you want to draw a p-type material, so what is p-type material? Is n-type. P-type material, the impurity is These both are same. Okay. P-type material has the impurity is the negatively ionized. Here we have a hole. Hole. So this is a hole. Okay. So this is a representation of P-type material. Okay. Here the concentration is Na. Na atoms per cc per centimeter cube. Cc means centimeter cube. And assuming each atom has a one hole, assuming each atom has one neighboring hole or one hole, p-type material has the n holes n holes per centimeter cube. Okay, Na is the number. So number we will discuss, but the number later. So this is your schematically. So generally you either you draw like this or you draw by holes. So these are holes. So this is the p-type material. Okay. Now I want to make a junction with these sections. Okay. Let me check whether time we have time or tomorrow I will discuss. Okay. So let us stop here because if we go now, it will take time because I want to do some derivation also. Although you will do that in solved part, but here just for completeness, I will do some small derivations. Okay. So when you bring this n-type and p-type material, what happens? Okay. How does what kind of processes happen? That processes we'll discuss, and tomorrow we'll see how junction is formed and how we'll see IV characteristics of the junction, and then we can start our main electronics syllabus. Okay, so I'll stop here. Thank you.